I did not even look. Oh, you don't look here. You look. Oh, yeah. So there is volume right there. So this is kind of, if you don't have any questions, I'm going to kind of do this to let you have an idea of what really happens kind of out there. And this is probably even on the FE somehow. I'm not sure how they do some of the exam now. So let's say you had something like that, like this, say a solar panel that water is pulled out of your swimming pool, goes through, and, if you want to find the delta T, you'd go to heat transfer and find out some stuff here. But what we're interested in, sizing the pump. And so, last time I said, oh, it's a 1-inch PVC pipe. I made it 1 inch because it'd be kind of small. Because otherwise, if you make it too big, the pump, your pump becomes funny. So I think I figured out that it was about a 230 foot of PVC pipe. So if you write Bernoulli's equation, and I think my ink pen, yeah, that's probably good. So pick anywhere you want. It turns out like a swimming pool. It turns out the particle will go all the way through the system and end up back there. So it sounds weird and bizarre. Oops, Z1 plus B1 squared over 2G minus, okay, let's try that again. Minus, okay, F L over D, V squared over 2G plus whatever head the pump is supplying. Okay. And I'll say HPUMPs to designate, this is supplying a head in the pump. And we're going to just pick one of these to determine this in a minute. And you're going to go all the way around. So when you go all the way around, you pass all these losses, you pass the gain, going through the system and back to the same spot. So believe it or not, you end up at the same spot, exact spot, a closed system. So it turns out this thing and that thing just cancel. It doesn't matter where you pick, as long as the particle ends up back where it was. So you get something kind of boring, and what you get is the head of the pump is offset by all the losses. Now, there's two ways to do this. Now, what I did is I said that essentially the solar panel itself has 150 foot of 1-inch PVC pipe winding back and forth through it. You might also find it has a KL, a loss factor. And if you had a loss factor here, all you would do is you'd say, sum of all the loss factors times 2G. Now, I didn't do that, but if you did that, so a heat exchanger could have a loss factor, but it could also have an effective length. So in our case, I said it was about, what did I say, 150 foot? So essentially it was about 150 foot equivalent loss to about 150 foot of pipe. So if I added all this up, my 150, better not mess with that. My 150, my 50 foot, 20 and 10 foot total, I end up with, what did I say, 230. So I have to offset, for this particular case, I have no KLs, KL equals 0. But if I did have some KLs, I'm going to just say for right now they're 0. So I have length of 230, diameter is equal 1/12, G is equal, 32.2 or 174. I don't have my pump and I don't have my F. So what I'm going to do is I'm going to do something interesting here. First thing I'm going to do is go after my pump diagram. And I think I can hold the control key down. No, I can't. Okay, so how do I select that? Don't do it that way. Text, text, text. There's got to be home. View. Okay, I know how to do it at the house. What? I can't. Oh, come on. Here, let's see. How do I do this? That's bizarre. Okay. Okay, let me look around. Do you see a text thing in here? Oh, jeez. Let's insert home. But, well, I guess I'm going to go back to the internet. And I'm going to go find. Hey, wait a minute. There I was at Granger's. Okay. Gosh. Sorry, I'm having to search this back out again. Yeah, centrifugal pumps are just fine. Now, I was doing something named Google. There you go. Okay. Just how about, I don't know, straight centrifugal. I don't know which one. Let's just do that one. So, got a lot of them here. I'm just gonna pick one. View product details. Is it gonna launch it or is it? No, it's not. Oh, this one does something interesting. Okay, so this is one way of doing it. Okay, so this one has a list of maximum gallons per minute at 40 foot. So what I'm going to do, and that is 58 at 40 foot. So what I'm going to do is I'm going to build a pump curve. So, wait a minute. Hello. Okay. So this is a tedious behavior here because now, okay, hello. It is not listening to me. There we go. So I'll just drop. What did I drop? What? That's interesting. This is bizarre. Well, let's do this then. We love MATLAB. Here. We're going to put a list of gallons per minute and then the associated feet of water. So what I'll do, gallons per minute, 53, 49, 45, 39, 31, 22. Okay, and that's all I got. So that'll give me the gallons per minute of water. Now I got to do head. So how about do H? Call it just H. So that was at 60, 70. I guess they all go increasing by 10. 80, 90, 100, 110, 80, 90, 100, 110. So if I plot, okay, along the basis, I want along the X, I want gallons per minute, and I want the head. And so you see kind of a pump curve. The only difference is I got one item, which was the maximum head. Let's see if I can find it. I'm sorry, maximum. Oh wait, there's a 40. and a 50 as well. Okay, I didn't see this. So there's a 40 and a 50. I'm going to go back and there's also the maximum head 58 at 40 feet. Oh, it's listed right there. Okay. So I got 53, but then I got 58 and I got 56. Then I have to go back and add the head of 40 and 50. Now I can plot it. So there's my pump curve. A couple of things I could do. I could mimic that pump curve and do a quadratic out of it. Let's try that. So if I were to do that and list this. Now, this is the art of engineering. This is not really, it's not going to be perfect. C1 minus C2 Q squared. So if I want that in gallons per minute, and I want this, the head of the pump, the one thing I don't have that he has is the stalling. Let's go back and see if he says, do I have the maximum pressure? Do you see like the maximum pressure anywhere? Maximum pressure of the pumps, 125 psi. That's bizarre. I hate the way they do that because they listed it. Oh, here, maximum head, 118. So 118. So if you wanted to include that, oh, here he has the thing too. Anyway, it doesn't matter. I'm doing it this way now. So the maximum head occurs, what did he say, 118. Okay, there's my head, 118. Go ahead and list that, but that occurs, that's the head, occurs at gallons per minute, will occur at 0. Now let's plot that. Okay, now I got to find the plot. So effectively what happens here is if I shut the valve off, in other words, if I take this pump, put it on the ground somewhere, so say you're testing it, you got this pump, and then what you do is you put this really nice valve on it, and somehow you measure the flow rates. So there are many ways to do that. So you close the valve completely off, and the water level, it's almost submerged, so there's not much height difference here. If you close the valve off, the pressure that it's able to supply was, what was it, 118? 118. So the question is, if you're looking at, okay, so the head maximum is equal to 118 feet of water. Turns out that if you want to know the pressure, so H is equal to, or gamma H is equal to the pressure. So if you got the H and you want to know the pressure, you just, I guess you could put 62 here. Here, I'll do it this way. 118 feet of water, 62.4 pounds per cubic foot. But that'll give you square feet. But if you want it in this, you would get that. So what is that equal to? 118 times 62.4 pounds. 62.4. Then you could do that, but that's too large. 144. 51. Now, already you see a problem here. This is the maximum head supply. Now it says maximum pressure pumps. So that is not the same thing as this. So this thing apparently can push out, where did it go? Oh, here we go. It can apparently push out, and I've already forgot, what was it? 51 PSI. It can push out that much. The pump curve itself sits in here and looks like that. Let's see how close we came to it by looking at the website, and let's see. Maybe that would be the one. Technical brochure. Okay, so is it this one? Now let's see. I don't know what model I'm looking at. Manufacturer's model number. Oh gosh. 1BF. Yeah, I don't know. Commercial water. It looks like I was pretty close to that first one. And since that's the only thing there, I'm going to go ahead and assume that's what it was. So it looks like I got about 120 drops off. And let's see. Do I drop off to like 60 at 60 gallons per minute, close to like, how do I put my curve up there next to it? 60, that looks pretty close. So my MATLAB shows me at 40, close to 60. So if you kind of see it, it's kind of that point. Is that the same as that? I don't know. I don't quite make 60 and I don't quite make 60. I hit it 40 and that's 40. So I don't know. So it looks to me like I'm tracing out that curve. So that being the case, what's the next step? The next step is kind of difficult and not difficult at the same time. One of the things about this is you don't know the flow rate. So let's do this if I can. Let's see. Is it F11? Makes it full screen. Can I do a snap there? Apparently I cannot. It doesn't let me do that. So how do I do this? Okay, F11. I gotta have the lower part. Let's try this. Okay, so let's try that. Why is it not working? Huh. Okay, well then we'll do it this way. No. Okay. We'll just, actually, you know what? I don't need the meters. So I can just grab the feet and the gallons. I'll drop it in here. What is the other? Oh, I never said anything about that. Okay. That's why I didn't. Okay. Okay. Edit, copy, paste. Where did it go to? Paste. There we go. Golly. So it turns out what's going to happen is, think about it like this. This is a battery and the resistance. So this is all the pipes and this is the pump. But it turns out as you push more flow rate through there, VRQ, as you increase, you're going to increase the resistance. And it turns out that it looks something like this. It's kind of semi to quadratic, but not quite. So if you're listed, if you're basically going to say, I'm going to be between here and say 60 gallons per minute, what will this pump? So I'm going to use this upper pump, this one right here. What would it look like? Well, first things I'll do, if I have 10 gallons per minute, how many cubic feet per second is that? So that's a good question. I think there's a number 480 in here, but let's see. GPM to, there we go. Okay, so I'm just going to put in 1. Well, yeah, you know what? That's a lot of numbers, so I'm going to put the 1 in here. Okay, there it is, 448. I'll copy that one. So how about 448? We'll do it like that, 448.83. So 1 cubic foot per second is equal to 448.6 gallons per minute. So if I want this in cubic foot per second, I do that. Now, what I'm going to do, I'm going to do something really interesting. I'll try to do as much as I can. So, how about we do flow rate? FR is equal to flow rate, and I'm going to do it for 10, 20, 30, 40, and 50. Just to get an idea of what it looks like. So, I'll do FR now, divided by 448.6, and that is the cubic feet per second. So it's fairly small, but turns out, let's do the one for 10. So 10 gallons per minute will give me 0.0223 cubic feet per second. Now, that's velocity times area, and the area is not so big, so it's the diameter pi 1/12 over, now that's squared, but that's, I guess I could do it in the radius. I'll do it in the radius. Well, I could do it this way. Okay, so the area of a pipe is equal to pi r squared, or pi d squared over 4. And that would be related to the 0.223. So I can get the velocity of the pipe, 0.223, divided by this area. So it turns out the area is the same all the time. So the area is equal to pi times 1 divided by 12. I'm having trouble with the shift key for some reason. Divided by 4. So there's my area. So if I want to know the velocity in these pipes, I need to go back and look and see what was my, I did FR, okay. So I'm going to do my area, wait a minute, that's the flow rates, and then divided by the area. That's my velocities in feet per second. Okay, so I'm going to take the first one, or shoot, I only have 5 of them. So this was equivalent to, on the drawing, taking the value here, 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 and here. And that was it. So I'm basically going to find the value of these points to map out this curve. So what I'm trying to do is trying to get an approximation of what this looks like. Now it's not going to be this, but I'm going to go back in and do this for each one. So what I'm going to do, go back and just do a copy here, and I'm going to say, how about that? Turned it sideways, which is okay. So here's my velocities in feet per second. This is in feet per second for gallons per minute of 10, 20, 30, 40, and 50. So now what I need to do is I need to find F L over D, V squared over 2G, the loss in the pipe system for each of these flow rates. And so that's easy enough because it's 230 feet of pipe, diameter 1/12, velocity. Well, that's the number that goes in here, and then 2 over 32.2, but I don't know the F. So I need to know F for every one of these. For V equals to each of these numbers, I need to know what F is for each of these numbers. Okay, so let's just do one of them. Let's do this one. And here's what we'll try to find. We'll go here and try to find it. There's a Moody diagram calculator. Here, we'll do that, and we'll do that one. Here's the Moody diagram calculator, and there's, oh, where's the Moody diagram? I don't know what that is. Okay, well, I just want to, here, Moody diagram chart, here. Because when you're in the FE exam, they give you the chart. They're not going to give you a calculator. Okay, that's a good enough chart right there. So what we need to do with this is we need to find the Reynolds number, come up and hit the diagram and come across and read off an approximation of what the friction factor is. So we will, and we have to use the relative roughness here too. Since I specified PVC, it's going to be the lowest one there. Let's see, if I move away from this to another, oh, it does go away. Okay, so I need to find Reynolds number. So given the velocity, so here, I did not specify that being the velocity, but I will now. That's the velocity. Now, the Reynolds number is nothing more than rho velocity, diameter of the pipe over mu. So that's the 1/12. We're going to assume this is going to be water, so rho is going to be 1.94 slugs per cubic foot, or 1,000 kilograms per cubic meter. This, for water, is roughly 3.4 e to the minus 5. That's what he uses throughout the textbook, but that varies a lot with temperature. But that's what I'm going to do here. So if I go into this, I can find the Reynolds number on all of these at once. Rho 1.94 times the velocity, which is a vector, times diameter is 112, divided by 2.34 e to the minus 5. So I get all these numbers. And shoot, I don't know how to actually list these out. How about doing it like this? Let's do that. Okay. This way I can see them to 2 decimal spots. But I can't, can I copy them? No, it'll copy. So here's my Reynolds numbers. Shoot. There's one set of Reynolds numbers. Here's the other. They're not very high. So I'm a little disappointed here that they're not that high. But, you know what? I could still monkey around with this. So my Moody diagram, where did it go? There it is. So I've got 2,000, 4,700, 7,000, 9,000, and 11,000. So I got 2,000, which is going to be, well, it's in this whole gray area here. She'd already forgotten what the other one was. 4,000, 4,700. It's going to be maybe right around in here. 7 and 9. So if this is 1,000. This is 10,000. So I guess I'm still short. Okay, 7 and then 9. 7 and then 9. So somewhere around here, somewhere around here. And then I guess I'm at like 11,000. So I'm somewhere maybe right there. So I've got some values kind of like this. So it's like 0.05. 0.04, 0.03. I'm just going to do that. So this is kind of getting the first ballpark. So I'm going to say F is equal to roughly 0.05. And that's very tenuous because that's in a transition region. What did I say then? Oh, it disappeared. Did I make it go away? Oh, there it reappeared. 0.04, 0.03. I'm just going to get a ballpark. And did I go down to 0.02? No, I'm just going to get ballparks. So I'm going to say it varied pretty much like that. If that's the case, now that I've got this, roughly, this is just a rough estimate. Here's what I'll do. I did not pick, so already you can see I didn't pick a powerful enough pump. I can't even get into I can't even get to the point of pushing myself out of the laminar region. So this is my Reynolds number. That's approximate. I'll say very approximate. Now I'm going to take these F's. I'm going to multiply times 230, 1/12, which is this. V squared, which I'll list them out this way, and then 2, and then 32.2. And you know, since these are so approximate, I'm just going to take for all of them like 0.04 and see what we get. So I have my velocity. There's my velocities. So what I'm going to do is I'm going to take the head loss equaling to, I'm going to basically take 0.04 times 235 foot of pipe divided by 1/12 the diameter times the V squared divided by 2 divided by 32.2. So you can already see 0.2, 0.8. This is not good. Here's what so I have a terrible design here. Okay, so I'm going to basically say, I'm going to try my best to list these out one at a time. HL in my cases are going to be, this is 0.2, 0.8. I mean, this is awful pump design. 1.79, 3.18, 4.7, 97. Now, here's the worst part. Okay, I have this back here. This is awful. Here's why. I never got past 5. No. I never got past 5. So my system curve looks like this. So it's not a good match. This pump and that is not a good match. If it was a good match, what it would look like is this. Here's my highest efficiency right here. So the perfect system curve for this thing would look kind of like that. So this is reality, and this is reality, but they don't go together very well. And so it's not a good pump for this. And so this is, I should have pre-done this to pick a better pump, but I didn't. Had I done a better job, I would have known that this pump would not match this system curve very well. I mean, you could turn it on and get it to do something, maybe. I don't know since they went to here, at least they ran it to 60, I think. I didn't even calculate it 60, so I don't even know what it looks like. But I don't think it's a good match. I wouldn't, if I was given that choice, I wouldn't buy this pump for this thing. So this is what you really would love to see. So I've done an awful computation here. So maybe what I'll do, today is Monday, so maybe what I'll do is I'll come back and do this using a complete MATLAB script and show you how you could possibly go in and take several pumps and run them all against this. And the way I would attempt to do it is go in for the pump, and that's what I'll do next time. I'll set the pump up, head supplied by the pump, as being the C1 minus, and I wrote a plus, minus C2 times the flow rate. So what I'll do for a group of pumps is I'll find this number. Then what you have is head of the pump is equal to F L over D V squared over 2G. Okay, so that means all the losses have to equal to the gain that's put in by the pump. But it turns out, if you put in this, you can actually do something interesting. Ooh, that's a D. V squared, but if you wait a minute, AV is equal to Q, which means V is equal to Q over A, which means I can take that out, and I can put a Q squared over an A squared, because I have a square here, and a 2 and a G. So already you see something interesting is you can do this. You can move this to that side and say C1 is equal to C2 plus F L over D, if I'm careful here, 2 A squared G times Q squared. Then you can say Q is equal to this junk. Okay, hopefully, here I'll do them all together. FL 2A squared DG, and then the square root of that. But the key is what is the, ooh, that's awful here. What is the C1 for the pump and C2 for the pump? And then once you get that, you really need to find this. So how do you do all this all together? And I'll kind of come in maybe next time, and I'll try to make this general. Then I'll make up some values of C1 and C2. Then I'll go find several pumps and list them for C1 and C2. See what you get out of it. What is the flow rate that you get out of the thing? So this is very confusing, but I hope this made sense. In essence, all you're doing in these is this. You're taking, well, first of all, you got to find your mouse. You're taking the diagram, and then you're putting the system curve on it. The system being all the pipes and everything, and it will end up looking kind of like a parabolic. And then wherever pump, if you bought this pump, you're going to sit right here and operate. If you bought this one, you're going to sit right here. If you bought this one, you're going to sit right here. So whichever pump you purchased, let's say this is the thing. If you decide to buy this pump, you're going to operate at that gallons per minute and in that head. If instead you bought this other pump, which this one is, essentially what's happening is each of these pump curves is basically either one pump operating differently with a different motor or a different diameter. So you might operate here. If this one, you might operate here. But most of the time when you flip the switch on a pump, it just goes to a certain speed and sits there. So it'll be one of these curves. So I will try to do that in a little better sense. So what I'll do next time is I'll say, what is the C1 and the C2 for that one? And what's the C1 and C2 for that one? And what's this? Turns out it's actually really easy to figure out. The C1 is the point that sits right here. And the C2 is kind of an approximation of how much it drops for how far you go out. So it's pretty easy. If you look at the head of the pump equaling the C1 minus C2 times Q squared, if you don't have any flow rate, then it tells you that this is where it intersects this axis right here, or this will be the maximum. If you closed it off, this will be the maximum pressure that pump can supply. So this was very hitchy sketchy because I didn't design a good system and I didn't pick a good pump. I could have done a better job of picking a pump, but maybe I'll look at it and we'll try to see if we can do a better job next time. But pump selection and system design is very tenuous. Sometimes you get some really weird behaviors if you don't pick the right pump. Um, you can stall a pump. Sometimes you get, sometimes you can just, the other thing is you don't want it flowing too fast. Um, so that it's very delicate, but once you get it, you get the right pump, you're fine. You're just fine from then on. So I think I'm done. I've talked a lot. I don't know that I said much. Okay, let me see if I can figure out how to